Hello, everyone. OK, today we're going to be talking about some of my favorite debugging tools. The idea is you kind of have this like Swiss Army knife, except there are no sharp objects on it. Except some of them turn out to be sharp objects. Anyway, another opening slide I have for this talk is Linux debugging tools you'll love, which involves you talking to a charming penguin about network packets. This is like, there's a lot of programming languages stuff at this conference, right? And there's this question of like, OK, well, so I'm not going to talk about programming languages at all first. But like, one thing that like Haskell and like Fortran have in common is that like when they talk to each other, they might all talk using a computer network, right? And they're all using TCP. And so kind of the common theme to everything I'm going to be talking about today is everything I'm going to be doing is stuff you can use on any programming language. And we're going to be talking about like the interfaces that programs use to talk to each other. Kind of the setting for this is sometimes I'll log into a computer and something will be like terribly wrong, right? It'll be like, boom, today is an exciting day for you. And you're like, what's happening? One thing that I'm really starting to learn and to try to believe in is that like all bugs are sort of easy to solve. And I don't mean this in this way like, this is easy, why do you think it's hard? But fundamentally, like if you can figure out what's going on, and if you have like the right tools to look at it, you're like, oh, I see. I sent like panda instead of cat, and it was supposed to be cat. I get it. Like, and if you have the right tools, everything gets a lot easier to do. Sometimes I think I used to have this idea of debugging, like I just needed to be really smart and stare at the code and think really hard and be like, I am a genius, which happens occasionally, but not that often. It's much better to have the right tools. And in particular, if you're like not scared to like kind of like delve into what's happening with your code and like keep on like uncovering further layers of abstraction until you find out the real problem, it can be really valuable. So instead of the normal ways of debugging, where you read the code, and you add the print statements, and you know the language, we're instead just going to be wizards. These are some of our magical toolkit. We're going to talk about strace, Wireshark, perf, netstat. It's going to be the best. If you don't know what these things are, good. Please stay, because I'm going to tell you about them. And the kind of conversation that we're going to be having in this talk is the conversation where you're like, hello, which file did my program open? And the operating system will be like, it was wrong.txt. And you're like, oh, well, I can fix that. I'll just open write.txt instead. So it's like you're having a conversation with your operating system about what your program is doing. So this talk is going to be, we're going to do 3 mysteries. Mysteries are easier to solve if you invented them yourself. So we're going to be able to solve all of them. We have the case of the missing configuration file, the case of the slow program, and the case of the French website. And then there's going to be some extra stuff at the end, depending on how many minutes we have. More minutes, more stuff. OK, so let's do the case of the missing configuration file. One thing that often happens to me is I will write a configuration file, and I will start my program, and it does not work, right? And it could either not work because I did the wrong thing, or because I edited the wrong file. Who's ever edited a file and it was wrong? Like all of you. Perfect. Right. But like, how do you know, right? A really classic example of this is bashrc versus bash profile, right? It's like, if you edit bashrc, how do you know if it was the right thing? It's confusing. IDK. Actually, I guess I know now. Like, sometimes you can learn over time, but like, what if you don't know? You could read the documentation, but that's boring. So instead, we're going to use strace, which is literally my favorite program in the world. As some of you may know, I have an strace sticker on my phone. It's a whole thing. Anyway, strace is a program that traces system calls, right? I always like to explain what a system call is, because when I didn't know, it was a bad time in my life. OK, so the way system call works is you have like a proper gentleman, I guess, who's like, please, can you open this file? And then your operating system on the other side. Operating systems know about all kinds of wonderful things. In particular, they know how to open files. They know what a hard disk is. My program does not know what a hard disk is, really. It's just like, please, file, thanks. So your operating system will give you the file. And then your program will ask things like, please read some bytes from this file. You'll notice that I underlined in red open and read. That's because open and read are system calls, and 2 of the most important ones. So the way you run strace is you take strace and you run it on your program like bash. I asked it to just tell me about opens, which is what this -e flag does. And then it was like, oh, you opened .bashrc. And I'm like, perfect. It was bashrc. Done, right? Now I know, at least when it ran bash that time, that it only read this file, and it did not read .bash profile. So if I edit .bash profile, it can't possibly work, because that file never even gets opened. And then I'm done. I don't need to read any stupid documentation. Who wants to do that, right? It's not fun. I want to show you a little demo of strace, because it can be a little scary. So it looks like this usually. If this is like totally understandable to you, raise your hand. So some of you are like, I get that. Yeah, so one good thing to remember about strace is just like that if you don't understand everything, it's OK. Just like use grep judiciously, and you'll be able to figure out what's going on a lot of the time. It's OK if you don't know what like most system calls are. OK, so we won. An important thing to know about strace is it can make your program run 50 times slower. Don't run it on your production database. That would be bad. That's what you need to know. These are some of my favorite system calls. execve is a really great system call. It means when you're running a program. So one really cool thing that happened, I think my first day at work at my current job, like 2.5 years ago, is we had this script. And the script was running a lot of commands, and it was running the wrong commands. And it was this Ruby script, and I didn't want to read the code because it was boring. I was like, who wants to read the code? God. So we ran strace, and we were like, hey, strace, just like tell us all the commands you ran. And it just told me all the commands that it ran. And I was like, oh, that one was wrong. Should have been different. And then like we could really instantly see what was wrong, right? Instead of having to like read Ruby. Ruby is fine. OK, so you can read or write files, you can start programs, and you can do like network activity, right? You can be like, this is the server that I'm connecting to. And there are lots of other system calls that I love, but these are some of my favorites. There are a lot of really good flags. You can write output to a file. You can say like follow every other subprocess ever, and don't just like strace this one program. You can print the time that every system call got executed. It's really great. I like it so much that I wrote a zine about it. About how much I like it 2 years ago. You can download it and print it on my website if you want, or you can just read it. OK, right. Oh, yeah, so I said that strace is really slow. Another thing that you can use if you don't want to use strace because it's too slow is there's a thing called OpenSnoop, which is new as of Linux 4.4. I'm going to show you like a little demo of how you use OpenSnoop. It's just a script. I just run like sudo OpenSnoop. And then we're just going to see what files are being opened on my computer right now. Oh, man, what's happening? Who knows? Right? It's like Google Chrome. Google Chrome is doing something. Browser blocking. What's that? I don't know. So this is kind of fun. This is a program which just shows you what programs are being opened. You can also tell it, like, I'm only interested in, like, one. Like, you can tell it you're just interested in, like, one specific program. And then it'll just show you what files that's opening. And OpenSnoop is good because it's fast, and strace is slow. And if you go to this GitHub repo, you can find out how to get it. But it only works on pretty new kernels. OK. It works using something called eBPF. Brendan writes a blog where he's basically like, so excited about eBPF. If you want to know more about it, you should read his blog. And then you'll be excited, too. OK. Next up is the case of the slow program. So we have 3 slow programs. 3. One is slow because it's using too much CPU time. One is slow because it's writing too much stuff to disk. And the last one is slow because it's waiting for a slow server. And we don't know which one is which. I mean, I do, but you don't. And they're called things like Mystery 1, Mystery 2, and Mystery 3. And we're not going to figure out which ones they are by reading the source code. We're going to figure out which ones they are by being wizards, obviously, because that's the whole point of this talk. OK, so I'm going to run. They're all Python programs. I ran Python mystery1.py. And I ran this program called time, which tells you, A, how long the program took, and B, sort of where it spent its time. So the interesting thing about this program is that it spent 5% of its time on the CPU, right? Which means that 95% of the time, it was waiting. What are you waiting for? I don't know. So what we're going to do here is we're going to look into the Linux kernel soul. It turns out that this is a really easy thing to do, which really surprised me. So what you do is you find out the PID of your process. In this case, my process was 31728. And I was like, what is the Linux kernel stack right now for this process, right? And this is something you can just go look at. It's no big deal. This is a lot of stuff on the screen. So if we erase most of it, you're like, oh, TCP receive message. I know what that is. TCP is like networking and stuff, right? Great. It was the network. It was waiting for some kind of network stuff, IDK, right? But we now know so much more. We didn't need to read what the program was doing at all. And that's amazing. I have the server, which is just like sleep 2, return high, which is why it took 2 seconds, because it just like hangs out for 2 seconds before doing anything. Perfect. So that was super easy to do. We just needed to know that the Linux kernel will just tell you what it's doing. OK, mystery program number 2. This one took 2.74 seconds, and it spent 99% of its time on the CPU. This one is like not really a big mystery. But I wanted to point out that like not all problems can be solved by doing this kind of like by looking at system calls. Because if you're on the CPU, you're just like adding stuff up or something, right? The operating system doesn't care, other than like it just needs to schedule you to run on the CPU. So the answer here is use a Python profiler, right? I don't know what's wrong with you. I don't care. And in fact, what this program was doing is it's just adding up 14 million numbers. Which in Python takes 2.74 seconds, which you might interpret as either computers are fast or slow, depending on how you feel about how long it should take to add up 14 million numbers. I have a whole game. Anyway, program number 3. Program number 3 is, it says, oops, 94%. So you might be like, Julia, 94% is basically the same as 99%. This is the same as before. And I would be like, good observation, but you're wrong. The reason that you're wrong is that it splits up the amount of CPU time into user space time and operating system time. And this is kind of interesting, right? So it's not really spending any time in user space. So the program itself isn't doing anything, but the operating system is spending all this time doing stuff. What is it doing? What's happening? Why? We're going to start out by running dstat, which is one of my favorite things to run. And what dstat does is it prints out how much like disk and network and CPU you're using every second. I have this demo slide because I'm supposed to do a demo now. Oh, no. OK. So I'm going to start this, and then I'm going to run dstat really fast. And then hopefully it'll have worked. Yeah, totally. OK, cool. So this is printing out. There's read and write in the middle there. Let me close this. And then I can point to stuff before it goes off the screen. No, Control-C, Control-C. OK, so in this write column here, you can see that it wrote 455K, 200 megabytes, 300 megabytes, 300 megabytes, and then it stopped writing stuff. So like somehow we instantly know what this program is doing, right? This program is writing stuff to disk. And like we don't care that it was written in Python, right? We know that it wrote 300 megabytes to disk that second. So that's cool, right? Like we've already learned a lot. But what's with the CPU usage? It's not that hard to write stuff to disk, is it? Why would it be so hard? What's wrong with you? So you might know who uses top to figure out what's taking up the time on their computers. Who uses htop? Htop is really cool, and I love it. Who uses perftop? Perftop is one of my favorite things, and we're going to talk about it now. Perftop is something which you can use on Linux. Perf is a program you can install. And basically what it does is it can tell you which functions are running slowly on your computer. So instead of which programs, which functions inside those programs, which is kind of crazy, right? So I'm going to start perftop right now. And yeah, OK. And then I'm going to run my program, and we're going to see what happens. OK, cool, it's happening. So look up there. You see AES NI enc1 and eCryptFS write begin. Right? It's happening. Something's happening. What does it mean? But so we see we have a clue now, right? We have an amazing clue, which we did not have before, about why our program is slow. I copied this here to make it bigger. So what does AES mean? Encryption. It means encryption. I was writing this file to my home directory. My home directory is encrypted. So it's a lot of work for it to write to my home directory. which is really interesting, right? It's like suddenly writing to disk is not easy anymore if you're writing to an encrypted file system. Fascinating. OK, new mystery. The case of the French website. I live in Montreal, which is a bilingual city. So if you go to a website, it could show up in either language, right? And like, how does it know what language to show up in? Oops, no, I lost my slides. Whatever, that's fine. They're here anyway. I'm so prepared. OK, so I have this website on my computer right now. And if I go to it in my browser, it says, hello, welcome to Strange Loop. Yay, everything is amazing. If I go to it in my terminal, what? Why doesn't it work? Then it hates me? Is that what's happening? Let's find out what's happening. OK, now it works. No problem. So if I go to it, if I get it with curl in my terminal, then it's in French, right? But this is the same website, right? It's in English here, and it's in French here. So like, what's happening? Why is it doing this? I don't know. I'm upset. So what I do to find out is there's this program called ngrep. Ngrep lets you grep, is grep for your network, literally. So grep searches a file, ngrep searches your network. And I'm just going to print out some of the network packets on my local network. So I start printing stuff out. Right now, there's nothing happening, so it doesn't print anything. Great. Something happened. Let's ignore that. That's not important. OK, and now you can see like, bonjour, bienvenue à Strange Loop, right? Has happened. And then I'm going to load it in my browser. And then we can see that it says, hello, welcome to Strange Loop. OK, so that was the response here, right? This thing is the response. What was the request? So this is the browser request. And this one here is the boop, boop, boop. This is the curl request, right? So it's like get HTTP 1.1, host, localhost, udrage, and curl, blah, blah, blah. And then Google Chrome said a lot of stuff, right? So curl was just like, website, please. And curl was like, Google Chrome was like, I have a lot of things to say about how I would like this website. One thing it specifically said about how it would like this website is it said, accept language ENUS. So it said that it would like the website in English. OK, cool. I can do that. I can ask for a website in English, right? Why does this website hate me now? I don't know. We would debug that, but we will not. Oh, it crashed. Why did it crash? That's so interesting. No, not interesting in the middle of a demo. Computer. OK, great. So now that we're not worrying about the crashing web server, which is yet another mystery, we're going to get the website. And now it gives me the website in English because I asked for it in English. And so this was kind of fun, right? Because like often, like programs are deterministic, right? Or they're not deterministic, but they're logical. And generally, they respond to the inputs you give them. So if you just look at what those inputs are, sometimes you can figure out why they're wrong. Great. How are we for time? Perfect. Amazing. We're exactly where I hoped we would be. OK. So the next thing I want to do is talk about perf. Perf is a program for Linux that I think is really kind of like tragically misunderstood. The reason it's tragically misunderstood is that it's pretty badly documented. And it's hard to figure out what it does. It does a lot of different things. And it's, in general, a tool that you can use for performance analysis. And kind of the reason I think that perf is interesting is like, well, it's pretty useful, right? Like you can run perf top on your computer to debug your programs. You can especially do that if they're written in C. You all might be like, I don't write in C. Why should I care? An exciting thing about perf and perf top is that you can use it to debug your programs also if they're written in Java or in Node. So there's a program called like Java Map Agent, which can tell you, which will like tell you actually which Java functions are running on your computer, like through perf. And Node has kind of the same thing. And I think like this idea that you can just like always see what's happening in your program at any given time is like really powerful, and it makes you want to build that for other like programming languages that don't have this. Anyway, but what's perf? How does it work? It has 3 different kinds of things that it does. One of them is it has hardware counters, which I'm going to explain. It has a sampling profiler, which is what we've been looking at, right? And it lets you trace things. So I want to talk for a second about sampling versus tracing. So sampling is when you have a program that's kind of slow. You want to know why. And you take a bunch of little snapshots, right? So you're like, OK, you're running this encryption function. OK, you're running the encryption function. OK, you're running the encryption function. OK, you're running the encryption. OK, OK, OK. And you're like, I guess it's just all the encryption function all the time, right? So you don't keep track of every single thing the program does, but you take samples often enough that you can get a really good picture of what's happening. And this is the way a lot of profilers work, and it's incredibly useful. But sometimes you have something that happens pretty infrequently. So I used to think that if something happened like 0.1% of the time, is 0.1% of the time a lot? Who thinks it's a lot? Not many of you. Some of you think it's a lot. So sometimes it's not a lot. So 0.1% of the time is like 1 in 1,000 times. And if you work on like a little small thing that not a lot of people use, maybe that means it happens like once every few days and doesn't really matter. But if you have billions of things, then 1 in 1,000 times is a million times, right? And so if something happens billions of times a day, and it's broken 0.1% of the time, it means it's broken a million times a day, right? And that can be really bad. And the bad thing about sampling profilers is if something is happening kind of infrequently, you'll often miss it. And so it's really important to have tracing tools, because tracing tools are tools that tell you everything that's happening, right? So you're like, every time this weird thing happens, tell me everything about it. And this is why I love log files. This is why I love tracing systems. And then you can be like, OK, this thing happened only 4 times, but all of those 4 times I'm like really concerned about, and I want to know everything about that. And I used to spend a long time trying to debug things with a sampling profiler, which would just show me like the general distribution, when what I needed to be doing was using a tracing tool. So it's important to know which one is which. OK, we're going to start out by talking about hardware counters. Which are another different thing entirely. OK, so I think this is really fun to know about. I mostly write Ruby. This is not that important if you write Ruby. But I think it's good to know how fast computers really are. Dan is going to yell at me, because I'm going to get this wrong. OK, so your CPU is right next to a cache called the L1 cache, which is extremely close to it. And it takes about like 0.5 nanoseconds to get something from the L1 cache. It takes like 200 times longer, just like this eon of time, to get to RAM. And if you're working on a program that's really performance sensitive, you actually care about this. And so 3 years ago, someone was telling me, they were like, Julia, it's important to use your caches efficiently, you know? And I was like, how do you know if you're using, like, this is this tiny thing inside my CPU, like, where even is it? I can't see it, right? Like, how am I supposed to know if I'm using my L1 cache? This is stupid. Like, this is not helpful. This is just like some weird abstract idea. So it turns out that it's not a weird abstract idea, and you can actually know exactly how many times your L1 cache is being used really, really easily using perf. And oh yeah, there's this great thing called latency numbers every programmer should know, which you can read and try to remember. I cannot remember these numbers, really, but I try to read it every so often. And I'm like, yeah, OK, read 1 megabyte sequentially from disk. OK, 20 milliseconds. OK, like, it's kind of hard, but it's good to think about. OK, and the way you can figure out about your L1 cache misses is you can use perf stat. And you're just like, hey, perf, tell me how many L1 cache load misses LS had when it ran. And it's like 40,757. And you're like, OK, great. And like, the reason I think this is interesting is not because this is something I use every day, but I find it really helpful to remember that like my computer is really fast and has all this really smart stuff in it. And I'm like, OK, if I ever need to know about how my L1 cache works, like, or like how to optimize that, that's like that's somewhere I could go, right? And these tools are available, and this stuff is happening in my computer. And it's like, it is ran in 0.004 seconds. And I'm like, OK, there's no problem. Like, I do not need to optimize this. Cool. So we know hardware counters. Let's talk a little bit about the sampling profiler. Do I have so much time? Yeah, I can maybe even talk about how it works. OK, cool. So perf has a sampling profiler, which is what happens when you run perf top. So what you do is you say, hey, please perf record this function, right? -g is extremely important to flag to perf. It means you collect like the full stack trace, and it makes a really big difference when you're trying to debug. So you want to record what's happening. And the way this works is there's this like subsystem in the Linux kernel, which will like, when your program is stopped, like collect information about what it's doing, and then like send you the information. So there's actually like a ton of work that went into like making this a thing. And it will create this file called prof.data after it's recorded all this sampling information. And then you ask it for a report. You're like, what were you doing? Find what was going on, man? And it's like, bleh. Right? It's just get dense. And it says that I find get dense kind of hilarious because it's always like it's like a dentist. I don't know. But it means directory entries. So it's spending a lot of time doing things like going through directories and figuring out what's inside them and going over them. And you can see like encryptfs read dir. So it spends time like decrypting stuff because I was doing this in my home directory, which is encrypted. Cool. This is a little hard to read though, because I'm like, what is really happening? I don't get it. Therefore, we have flame graphs. Flame graphs. Flame graphs are one of my favorite things. The way a flame graph works is it means that you spend all this time in this function, and then it called that function above it, and it called that function above it, and it called that function above it, and then it called encryptfs build dir, and then that kind of like narrows up, right? And you can see like the shape of how your program is spending its time. And this is also, like this isn't just a perf thing, right? This is like a generally a nice way to visualize performance, which I really love. I tried to like sketch this out a little more here with this hand-drawn flame graph. So you can imagine you spend like all of your time in main, and then 20% of the time you go over to the panda function, but 80% of the time you go to alligator, and pandas like, and then again like 10%, like half of that is eating, and then like anyway, 28% teeth. It's supposed to be a helpful diagram. I don't know. And flame graphs don't just work with perf. So there's actually, these are all generated by this tool called flamegraph.pl by Brendan Gregg. And there's a pretty simple input format, and a lot of like profiling libraries can actually generate that format, or you can just make them do it. It's really simple. You just print out a stack trace and put a 1 at the end. And then it'll make like a really pretty SVG with all these like colors. The colors don't really, as far as I can tell, they don't mean anything. They just make it look like fire, and you can tell the things from each other. Maybe they mean something. I don't know. The last thing that perf can do is trace things like system calls. I mostly put this in because it's kind of exciting, and not because it actually seems to work that well. So there are a few ways. We talked about 3 ways to trace events, right? There's strace, there's OpenSnoop, there's perftrace. There's another thing called ftrace, but we're not going to talk about that because A, I don't understand it. Well, that's the main reason, actually. So we're going to talk about perftrace. So strace lets you take a process and see what system calls it's writing. Perftrace also does this, and it does it quickly, but it also doesn't work. It's like, sorry, I lost all these events. And I'm like, thanks, I guess. Like, at least you're telling me. I don't know. I felt confused about this, but I also thought it was kind of exciting. Because it's like nice to have the things you want in the same tool. But I was sort of, I don't know. I just did this yesterday for the first time, and then I decided to put it in this talk. OK, so yeah, you can trace different things, like system calls and page faults and scheduling events. OK, cool. We still have a few more minutes. So we're going to talk about more stuff. Great. So we talked about ngrep before, and how ngrep lets you look at your network traffic. And I really love looking at network traffic because, like, I work for things that are on the internet, right? And it's this like super great interface. A lot of the network analysis tools are extremely good, so it's really fun to be able to take advantage of them to figure out what your. So like one thing I really like to do is, let's say I'm on a computer, and something is like all these network requests are slow, and you're like, well, whose fault is that, right? Because it could be the client's fault. The client could be like sending the request, but then like taking a really long time to deserialize it, or it could be like the server's fault, and the server could be responding slowly. And you might not really trust like the metrics frameworks on either side. So one nice thing to do is just like drop down into like looking at the network conversations and being like, well, how long did it really take, right? From the time you sent the first packet to the time you sent the last packet. And then like no one gets to mess with the data, right? You can have like a single source of truth, because like the network is a really nice abstraction there. So I like to do this with tcpdump and Wireshark. tcpdump is a program that I was scared of for a very long time, like maybe 2 years. And then I realized I was like, oh, I can just save network traffic with tcpdump, and I don't need to worry about how it works. Maybe I can show you why I was scared of tcpdump for a second. Boop, boop, boop. So this is why. Because I was like, what is happening? Why does it say what? Oh my god! Like, right? Like, ACK1 win992 options nop. Anyway, so it turns out that tcpdump is still useful to me, even though I understand almost nothing in the output of that program. And the reason is that you can just use tcpdump to save network traffic to analyze later. One really amazing thing about tcpdump and about, I think, like network analysis in general, is for basically all of these tools, you can give it a filter, and you're like, I only want traffic on port 80. This is called the Berkeley packet filter, or like BPF. And it's this really nice language. It's super fast. So like maybe if you have like an extremely fast network card, you have to worry about running it in production. But generally, I feel fine about like running it in production, as long as I don't write too much stuff to disk. And you can just be like, hey, this is the traffic I'm interested in. Please like save it for me. You can filter out a lot of stuff. The filters are fast. They're compiled into like magic pixie dust or something. And it's really wonderful. And it saves it into a PCAP file. So PCAP is like magical chocolate chip cookies for packet analysis, which means that like every tool understands PCAP files, and they're wonderful. And then you can just save this file and copy it to your laptop and like peruse it at your leisure. This is a really great pattern. Like tools like sysdig also use this, right? You just like save what's happening, and then you go and analyze it later when you have like time and it's not like an incident and you're like, you can calm down. Oh yeah. And BPF filters are like pretty easy to write. You just like source IP this. Oh no, it's IPcirc. Anyway, I always get the order of those two things wrong. But the cool thing is it's either source IP or IPcirc, and then yeah, you just like try both, and then it works. Yeah, so you can just like source IP this on port 8080, and then it just works. Great. You can also just like print packets to your screen with tcpdump. Like you can be like, and then this is kind of like sometimes equally incomprehensible, but sometimes you can read the contents of the packet and you'll understand something. Like if I go to a website like that. No, it's not. There's too much noise. OK, that was a bad demo. That's what happens when you invent demos on the spot. OK, cool. So we're going to talk about Wireshark for 5 seconds, and then we're going to be done. So Wireshark is a packet analysis tool which looks like this. I kind of love it. I do not love what it looks like at the beginning, because this is confusing. Because there's all this stuff, kind of with tcpdump, right? But it's actually OK. And Wireshark is actually a thing that you can use if you like kind of like close your eyes and squint at it sideways and learn a few basic things about it. So one thing that you can do, I wrote like these like exercises for using Wireshark at some point to be like, it's OK, I promise. So you can just like search all your packets. And I was like, OK, I just want the ones that have get in them. And it was like, oh, there were 5. And I was like, oh, 5. 5 is a normal number. And I'm like, oh, they came from this IP, and they went to that IP, and that's it. And I was like, oh, that's so simple. And the nice thing about this is like this packet actually has like an HTTP request in it, and Wireshark knows everything about the HTTP protocol, and you can just go into it and see what happened. Another really nice thing about Wireshark is that it knows about other protocols and not just HTTP. So if you're talking to a database, like Mongo, for instance, it'll be like, I know what you're trying to query. I understand queries. And you're like, who are you? Are you a magician? And it'll be like, yeah, I'm Wireshark. I'm like a magical shark that knows everything about networking. And you're like, oh, goodness. Good thing you're on my side. So like Wireshark is really great. And it's kind of confusing, but that's because it's really powerful. And if you kind of like explore and click on things, it often works out. This is a neat thing you can do. If you click on like statistics and conversations, This is like the worst screenshot in the universe, and I'm sorry, but all the way on the right here, there are these numbers that tell you how long the whole request was. So it's like that one took 0.5 seconds. And I like to sometimes like download a PCAP file and then like say, Wireshark, please tell me how long everything took. And then it's like the slowest thing was like 3 milliseconds. And I'm like, oh, everything's fine, I get it. Like my other metrics thing was wrong. Yeah. So I guess my messages in this talk are like, if you learn your operating system tools, you can debug all kinds of programs that are written in like every programming language. One thing that happened to me once is I was sitting in a room, and someone was like, Julia, I have like a network performance problem. And I was like, OK, sounds fun. And they were like, it's an Erlang. And I was like, OK, sounds fun. And I don't know anything about Erlang, but I ran strace on it, and then it was like, blah, 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 lock. And I was like, lock. Lock is bad. And I was like, do you have a lock problem? And they were like, yes. And then they went in and they fixed their lock problem, and then the program was fast. And I was like, I'm amazing. I just So you too can be a wizard, right? And a lot of this stuff really isn't that hard to learn. Like it takes some time and some like experimentation, and sometimes you're like, what? Like, why is it weird? And what is a packet? But you can totally learn all of it. One thing that I did to help people learn it is I wrote a zine called Linux Debugging Tools You'll Love with a really cute penguin on the cover. My friend drew the really cute penguin, but I wrote the rest of it. And it goes through a lot of the stuff and like how you use it. And I hope that you'll read it. It is at jevons.ca/zines. Thank you.